All right. Hello, everyone. My name is Kritti Sharma. I'm a graduate student based at Caltech, primarily working with the Deep Synoptic Array team. DSA 110 is a part of the broader Deep Synoptic Array project, which we heard more about earlier this morning by Vikram. This particular array was built as a prototype array to test a bunch of new technologies for DSA 2000. And some of the primary key science goals for DSA 110 included understanding the origins of FRBs, how are their progenitor sources formed, what can we say about the physics behind such energetic radio bursts coming from extragalactic distances. And the second science case focused on using them as probes of precision cosmology, specifically trying to understand how are the baryons distributed in the universe, where are those more than 3/4 of luminous baryons which are not easy to detect at other wavelengths, and is there anything that we can say about galaxy formation processes and how the universe basically evolves. The array itself is based at this beautiful location in Owens Valley Radio Observatory, observatory which is in the middle of this valley in California. The array is designed such that there's a core which basically forms phased array beams to search for FRBs. So during the initial commissioning phase, we only had this east-west arm of the grid of 48 antennas, which was doing this phased array search for FRBs. And more recently, we've upgraded the array to include this north-south arm of the array, which is expected to almost double the rate of FRB detections with DSA 110 project. It basically comprises of 4.65 meter diameter dishes, which were spin formed. And the frequency band that we are searching at is between 1.3 to 1.5 gigahertz, which is kind of optimal because your expected scattering and other burst-related properties are expected to less influence your observed FRB burst. The field of view of the instrument is about 10 degrees square. So it was really optimized to search for a larger field of view such that you can find more and more FRBs. The maximum baseline for our instrument is about 2.6 kilometers. So we have about 15 outriggers within the array, which are basically used to help with arc-second scale localizations of FRBs. So every time a burst is detected, we save the buffer data for outrigger antennas together with the core antennas to enable offline analysis, such as doing or characterizing the burst properties like polarization properties, or to conduct high time resolution studies of the burst itself, and to also enable precision localization, which we used to do offline. Here you're looking at an example dish of DSA 110. Given the key science goals that we wanted to do or achieve with DSA 110, we had really put some stringent constraints on what technical design we expected from DSA 110. So we use these low-cost spin-formed dishes, which are steerable in elevation only, and all of this can be done remotely, and this one was built at OVRO itself. We also use these low-noise amplifiers, which deliver an ambient temperature, noise temperature of about 7 Kelvin. So this is again the same LNA that was presented by Vikram earlier this morning. So we're using the exact same technology for DSA 2000 as well. Apart from that, we have this multi-purpose digital backend with all these high performance computations, which basically works in the backend to perform the search for FRBs, does full cross correlation, beam forming, and voltage recording. So all of this is basically fully automated for DSA 110. The commissioning phase for DSA 110 was as follows. So we were funded in 2018 by NSF. The preliminary and final design reviews were conducted in 2019. And of course, as any other project, there were delays because of COVID-19 in construction during 2020. Early in 2022, we began commissioning with the core of 48 antennas with 15 outriggers. And we ended up in a sort of extended early science period with that array. The recent update is that we have completed construction of the north-south arm of the core, and we are currently commissioning with this new addition to the existing array. And once this is operational, our expectation is that it should more than double the current rate of FRB detections with DSA 110. This is an example burst detected by DSA 110, one of the first FRBs. So you're looking at the waterfall plot and the corresponding SNR of the burst together with the PAs. So every time a burst is detected, we basically use calibrator sources within the field to correct for, to basically get all the antennas in coherence. And once that happens, we use these nicely localized VLBI sources within the field to perform astrometric corrections and to basically help us achieve arc-second scale localizations of FRBs. So here we are looking at the rough PSF of DSA 110 with just the east-west grid of the core. This is what a dirty image for an example FRB looks like. And once you perform the deconvolution, this is what the clean image of an FRB looks like. And then we use calibrator sources within the and outside of the field to basically perform astrometric corrections. So the plot on the right here is a demonstration of the accuracy of DSA 110 localizations. So we are looking at about 70 sources within DSA 110 data as localized in RA and DEC. So out of the 69 sources, there were only 4 for which the 90% confident localization region did not include the actual location of the source. So this is a demonstration of our localization accuracy, especially for bright sources within the field. So to summarize, DSA 110 has a field of view about 10 degrees square. And using all the outriggers, which have a maximum baseline of about 2.5 kilometers, we are able to localize FRBs to about 2 arc-second precision. So far, we have discovered about, I think, 70 or 80 FRBs, out of which a sample of around 30 to 40 FRBs is currently published. So here, what we are looking at is the cutouts of all the host galaxies discovered by DSA 110, organized in increasing order of their redshifts. You can see the DMs of the FRBs listed as well. The red regions here denote the 90% confident localization region. And the cyan cross here basically highlights the path associated host galaxies for each of these FRBs. So we've conducted optical as well as near-infrared follow-up for majority of these galaxies in our sample to basically be able to achieve better resolution and better depth in terms of imaging, as well as spectroscopy to measure the redshifts. So here I'm just showing an example burst that was followed up with Keck, which is a 10-meter class telescope based at Hawaii in Mauna Kea. So for this particular host galaxy, we had placed slit along this green line, and this is basically the localization region of this particular FRB. And here you can look at the examples spectrum of this particular FRB. So if we have more than 2 to 3 lines, then we can basically have a confident spectroscopic redshift measurement. I'm sure several of you who were also here in the last week for the school component of this particular workshop, you've already heard me talk in a great detail about how we go about modeling the spectral energy distribution of these galaxies. So really quickly, we do a joint fit to both the observed photometry as well as spectroscopy to derive basic host galaxy properties like stellar mass, star formation rate, etc., to basically try and understand what these FRB sources may actually be. Together with efforts from several collaborations, including work led by Shivani, Alexa, Mohit, Casey, and myself, we've together built a sample of about 50 to 60 FRBs for which we have very precise and better understanding of their host galaxy stellar mass and star formation rate. And using these, when we compare them with the background galaxy population of star formation rate, especially in work led by Alexa Gordon, we concluded that all the FRB host galaxies seem to be tracing the star formation main sequence of the background galaxy population, which is good, and it basically indicates that we might be able to find more and more FRBs at higher redshifts as the star formation rate density of the universe increases up to redshift 2. Furthermore, performing a more careful analysis where we compared the DM or the corresponding redshift and R-band magnitude distribution of these host galaxies with that of core collapse supernovae, which are thought to form most of the magnetars, we found that there's about 3 sigma deficit of FRBs in these low mass galaxies. And using that, we concluded that it's possible that there's a preference for higher metallicities, because if you compare the FRB population with that of background galaxies selected by star formation, there is about a 3 sigma deficit of FRBs in less than 10 power 9 stellar mass host galaxies. Our work has actually triggered a lot of interesting ideas from the FRB communities for what this low mass deficit may actually imply. And an example include this work led by Nick Loudis, where they commented that it's possible that there's a preference for a combination of star formation and stellar mass. So we should continue building larger samples of FRBs, especially at low redshifts, to better understand what these sources might be. Coming back to the broader question of the magnetar formation that we plan to answer with DSA 110, since about 85% of massive stars are expected to occur in binary systems, and metal-rich stars are also conducive to cause these unstable mass transfers, which lead to these magnetic massive stars, that might actually explain the origin of large magnetic fields in single star systems, as well as the formation of magnetars at the end of their lifetime. And independent evidence for the same actually also comes from work led by Miles Sherman in our group, where they tried to look for ejected or binary companions of magnetars in our own galaxy. And we basically didn't find any good candidates for companions, thus establishing that about 80% of isolated magnetars in our own galaxy must have formed through some sort of a stellar merger scenario. So that is pretty much where we stand in terms of our take on how FRB sources might be formed. However, this question of multiple formation channels still remains open, because if we compare the stellar mass distribution of FRB host galaxies with that of other transient classes, our similarities with type 1a supernovae and short duration GRBs still cannot be ruled out. So it's still possible that there's a fraction of FRBs that occur through these exotic formation channels, but still based on the rate arguments, we think that the fraction of FRBs coming from these formation channels must be very low. Thinking further on the formation channel question of FRB sources again, we all have together built a large sample of FRB host galaxy star formation histories. And using these, we should be able to put some constraint on the typical age of their stellar progenitor. And historically, this has been done by using the FRB or any transient's delay time distribution. So for example, in case of core collapse supernovae, this is what the delay time distribution looks like, where majority of the sources have ages of less than about 50 mega years, which is consistent with that of the nuclear fuel burning time scale. And there's this tail of sources which undergo core collapse supernovae that have probably gone through some sort of a stellar merger. Similarly, for short duration GRBs as well as type 1a supernovae, folks have used several forms of delay time distribution formalisms and star formation histories to comment on what their particular source age might be. So the idea is that we could perform similar analysis with FRBs. And we do have some initial results where we tested a bunch of models using DSA 110 host galaxies, sample of about 20 host galaxies. And there does not seem to be any strong evidence or a preference for one of these formation channels or one of these delay time distribution formalisms. So we basically need to continue building on larger samples of FRB host galaxies to nail down this question better. Apart from that, we do have a bunch of insights for for the rest of the community on how to perform such an analysis, because we found that such analysis can actually bias your characteristic age of the stellar progenitor, because the global star formation history essentially probes your median stellar population age, which could in principle be much larger or much smaller than your local environment of the FRB source itself. Pushing further in this direction, again using DSA 110 localizations, we are thinking of getting KCWI results, spatially resolved spectroscopy, to put better constraints on the ages of these stellar progenitors. Further highlighting work done by other students in the group. So in this work led by Miles Sherman back in 2023, we conducted polarizations studies of a sample of about 25 FRBs. And there we basically, you can see that, for example, in this waterfall plot, that the FRBs do exhibit these nice and complex spectral as well as temporal properties. And using a sample of about 25 FRBs in this work, Miles basically found that most of these FRBs seem to have a large linear polarization fraction, which might indicate that the emission mechanism for FRB sources themselves might just be intrinsically linearly polarized. Further, in work again led by Miles Sherman, they basically separated out the RM contributions from host galaxy and that of other components, including IgM, Milky Way, and burst local regions. And they found that there's a close to positive correlation between RM host as well as the DM contribution of the host galaxy. Furthermore, looking at correlations of the extragalactic RM with that of redshift, we found an anti-correlation. So both of these results combined basically push for the idea that most of this RM must be coming from the local environment of the source or the host galaxy's ISM itself. In this work led by Jacob Faber, we found one of the highest scattered FRBs as was discovered at the respective wavelength that we are searching at. So here we are looking at the DM scattering relation. So this is the standard hockey stick model for pulsars in our own galaxy. For this particular FRB, given its dispersion measure, it is fairly off this correlation for galactic pulsars and is heavily scattered. If you look at the specific sightline of this particular FRB, there seem to be two intervening galaxies sitting along the sightline at impact parameters of about 30 to 40 kiloparsecs. So it's possible that there were high velocity clouds in the environments of these galaxies, which led to such heavy scattering. So, but this discussion still remains open what caused this particularly highly scattered FRB. More recently, in work led by Miles, we are setting up an image plane search for not so fast radio bursts, which basically in this phase space of flux and search widths. So this is the DSA 110 FRB search parameter space, and Miles is working on extending it all the way beyond to 10 power 4 milliseconds or 10 seconds. So this is basically pushing to look for these long period radio transients, which we have evidence for a building population from ASCAP, CHIME, and a bunch of other instruments. Given the latitude or the specific location of DSA 110, we are also actually sitting at the same longitude as that of CHIME. So this means that we do end up with a couple of FRBs which are co-detected in both the instruments. And this is exciting because both CHIME and DSA 110 are actually operating at fairly different frequencies. So you can use these co-detections to put constraints on scattering phenomenon involved as well as the scintillation bandwidths. So there's this work led by Jacob that you should keep an eye out, must be coming out fairly soon this year. Shifting gears a little bit and coming to the second component or the second question that we were the most interested in with FRBs, which is to put constraints on how baryons are distributed in the universe. In one of the first works led by Vikram, we had put constraints on baryons in the Milky Way halo itself. So we found this FRB, which we lovingly call as FRB Mark, which was localized to a host galaxy at a distance of about 50 megaparsecs or a redshift of 0.01. So this is fairly close to Milky Way, and combining this particular FRB sightline with pulsars and Magellanic clouds, as well as M53 globular cluster, we had put constraints on the baryon fraction in Milky Way halo, which is less than 10% of the total Milky Way halo mass. And if you compare it with baryon fraction, which is about 16%, this is about 60% deficit of baryon mass in Milky Way halos. And this is consistent with hydrodynamical simulations like that of elasticity in G, which pitch that feedback phenomena can actually push out your baryons fairly outside of your R200. Furthermore, we have also detected a bunch of FRB sightlines, which are actually through massive galaxy clusters. So here are two examples in work led by Liam Connor, who's now based at CFA, where we found these two particular FRB sightlines with dispersion measures of 630 and 270 parsecs per cc. And given their respective host galaxies, the expected mean dispersion measure from their IGM contribution was expected to be order 100 parsecs per cc. So there's clearly a strong offset or a large excess in observed dispersion measure of these FRBs. And if you compare it, or if you look at these particular sight lines in terms of the galaxy number densities in the fields of these FRBs, then you can clearly spot this excess of galaxy number density. And this is actually two massive Abel galaxy clusters which these FRBs were originating from. So if you take example galaxy clusters in hydrodynamical simulations like elasticity and G, and try to construct their DM profiles as a function of impact parameters, then for these characteristic halo masses, which were comparable to these two respective galaxy clusters, the observed excess dispersion measure for their corresponding impact parameter was actually consistent with that of hydro simulations. So this basically pitches for the idea that you can indeed use FRBs together with other probes like SZ measurements or X-ray cluster measurements to better understand the halo gas profiles or halo density profiles. Finally, I would like to highlight in one of the recent works led by me myself, we studied the dispersion measure redshift relation, and we found that the variance or the scatter in the DMZ relation is actually correlated with the degree of clustering of baryons in the respective halos. So here, as an example, I'm showing 3 simulations, Astrid, Elasticity in G, and Simba, each with increasing strength of baryonic feedback as you go from left to right. And in the bottom, we are looking at DMZ relation in these simulations. So you can clearly see that as your halos become less clumpy or as your halos become relatively smoother, your scatter in the DMZ relation actually reduces. So with DSA 110 and existing samples of FRBs, we are working on putting constraints on the variance in DM as a function of redshift, and hence thinking more about how to put constraints on the strength of feedback in universe. You will hear more about this from me tomorrow. Finally, I'd like to highlight again one of the recent works by Liam Connor, where we studied the DMZ relation. And as I mentioned, the scatter in the DMZ relation depends on the strength of feedback or your partition of baryons in massive halos and IgM. So Liam used a hydro simulations based framework to put constraints on the partition of baryons into IgM and halos. And using that, we've put about a 10% constraint on the fraction of baryons in IgM to be about 80%. With that, I'd like to stop because I'm hopefully running out of time and leave my summary slide up here. Thank you.
Thanks, Kritti. Questions for Kritti?
Very good question. So the question is, how do we separate out the IgM and CGM contributions? So it really depends on how you define your halos. So for example, in case of elasticity in G, I think it's defined as R200 as a boundary between IgM and CGM. I think a better way of looking at it would be, instead of like partitioning the two out and leaving it controversial how the partition is, you could instead look at suppression of matter power spectrum. So I'll be happy to talk more about this offline, but you can actually look at correlations and variance in DM with that of matter power spectrum suppression. And in that case, you won't be sensitive to the definition of halo itself.
Okay. Definition of things, Kritti. So about the last part of your work, where you are going for this DMZ relation with simulations. So what is the present this thing from observational point of view? So do you have enough sample to constrain this DMZ relation and then compare that with what you are getting in simulation?
So with order 100 FRBs in terms of suppression of matter power spectrum, again, we should be able to put about 10 to 20% constraints on suppression at a scale of megaparsec inverse. So this is comparable to, let's say, that of KSZ from ACT, for example, right now. So in terms of like comparisons with different probes and whether or not we're competitive, I would say we are indeed competitive, but we don't have first constraints on such measurements that we could actually start comparing with different probes more meaningfully. I guess with elasticity in G specifically, here we used a sample of about 70 to 80 FRBs to constrain the variance in DM. And here we were again specifically using this partition to do the comparison, but we were specifically working under the framework of elasticity in G. So we haven't really done comparisons with other simulations in this case.
Any further questions from here? Anybody online? Okay, Ramesh, please go ahead.
To unmute myself. Yes, can you hear me?
Yeah, Ramesh.
Yeah, so thanks very much, Kritti, and a lot of interesting updates there. And I must confess that I have not been super up to date with the latest, a lot of these high DM FRBs. But my question is sort of related to the point that was brought up earlier. But I'm asking more from the perspective that with this, the current sample of or growing sample of high DM, high Z FRBs, do we have a clarity on where most of the scattering is coming from, IGM or CGM, or is it like a FRB dependent?
I think the belief is that most of the scattering actually comes from the host galaxy itself. But I'm probably not the best person to answer this question. There might be more experts in the audience on the subject. But I think the broad consensus is that most of the scattering is occurring in the host galaxy itself because it goes as 1 plus z to the power 4, I guess. So it has to be within the host for us to be able to detect, because it's also the observing lever arm that you need to account for. So there are a couple of effects which make us believe that most of the scattering must have occurred within the host environment.
Thanks. Yeah.
Any further questions? So Kritti, maybe I can ask one thing. We have seen that a nice plot of showing the fractional linear polarizations of all the FRBs. So do you see any kind of difference between the repeater and non-repeater, or is not kind of?
I would say that the at least like with DSA 110, we don't really have a statistically good sample of repeaters because the field of view is really small. It's just 10 degrees square. So at least for given our sample, we can't really like conduct such studies, but I'm not sure if Chime has already thought about it.